So, College Algebra, Section 1.3, Chapter 1, Section 3, Complex Numbers and the Quadratic Equations in the Complex System. First of all, what the heck is a complex number? Well, you can use your set builder notation. This can sometimes be very insightful. It looks like this: a plus bi, such that, so it's the set of all things a plus bi such that a and b will be elements of the real numbers, and I is the square root of a -1. This I is called the imaginary unit, and so they used to call these the imaginary numbers until they found so many concrete applications for them that they said, well, maybe we should just call them complex numbers. If you remember, the real numbers are made up of the rationals and the irrationals. Those are two separate sets. That's what made up the real numbers. They're subsets of the rationals. But there is a bigger set. This is when a plus bi, where b is equal to 0. It doesn't have that second part. It's just a real number. When b is not equal to 0, then you've got a bigger set of complex numbers. In fact, it's infinitely bigger, which we can talk about maybe some other time. But these are all these kind of numbers. I is sort of special. It's important to recognize that I squared, which is equal to the square root of a -1 times the square root of a -1, which you could argue is equal to the square root of a -1 times a -1, which you could say perhaps is equal to the square root of 1, which is equal to 1. But that's not true. I squared is defined as, then, a -1. When you square the square root of -1, you get rid of the square root, and we want that property because we want things to work right. The real numbers, everything works right. We want these complex numbers to add to that. So I squared is really a -1, and that's how you get square roots of negatives having some answers now. So I to the 0 is 1. Anything to the 0 power except for 0 is 1. I to the first is I. Pretty easy. I squared, we just saw, -1. And I cubed is really the I squared times I, or a -1 times I, or a -I. What's interesting here is I to the 4th is now 1 again, because you get a -I times I. Well, this is a -I squared, but I squared is a -1, so you get the -1, so you're back to 1 again. And this will keep repeating itself. And how do you figure out, and you'll be asked this on a quiz or a test or both, what is I to the 2021 power? Well, because these are the remainders, 0, 1, 2, and 3, when you divide a number by 4, that's all you need to do. Take 2021 and divide by 4. 4 goes into 25 times. 5 times 4 is 20. Bring down the 2. No, it doesn't go in that. Then you have 21. 5 times 4 is 20. And you don't do the decimal and keep going, you say remainder 1. Well, this 505 really has nothing to do with it. That's really how many times you're going through this loop. 0, 1, 2, 3, 0, 1, 2, 3, 0 to 1 through 3. This remainder, it tells you how far you go that last time around. So if we go with this extra 1 jump, we get I to the 2021 will be there down the road here if you kept going. So this is equal to I. I to the 2021 power is just I. Well, do you have to do this long division or anything? No. All you need are the last two digits. And all you need from that is the remainder. So, it can be something that you could do in your head, but because you want 4 steps, you probably want to show that on your work. So, we get to objective 1 then. We need to add, subtract, multiply, and divide complex numbers. And this is the complex symbol. That's C. So, add. Pretty easy, and it's easiest just to go with an example. 1 plus 2i plus negative 5 plus 4i. All you do is you add the real parts, that's the part without the I, and you add up the imaginary parts, that's the part with the I. The real and the imaginary parts are real and imaginary. So the 1 and the negative 5 give me a negative 4 for the real part. The 2i and 4i is really a positive 6i's. Subtraction is similar. If we take 1 plus 2i and we subtract negative 5 plus 4i. Now you can subtract your 1 minus a negative 5 is really 1 plus 5 is 6. 2 minus 4 is a negative 2i's. Think of that I like an x. You can combine i's. You can combine real numbers. Multiply is like FOIL. 1 plus 2i, negative 5 plus 4i. It's got a little twist at the end, though. 1 times negative 5 is negative 5. 2i times negative 5 is a negative 10i. 1 times 4i is positive 4i. And then 2i times 4i is 8i squared. Remember, I squared is a negative 1. So we have a negative 5 and 8 times a negative 1, or a negative 8, which is a negative 13. Negative 10i, positive 4i, negative 6i. So this now becomes part of the real part, because the I squared becomes a negative 1. The I gets this. On your final answers, you should never have anything more than an I. There's no I squareds or I cubes. That can be changed into a 1, negative 1, I, negative I. Divide. You never divide. 1 plus 2i over negative 5 plus 4i. You multiply both numerator and denominator by the conjugate of the denominator. The conjugate, leave the first part alone. We're going to do this both numerator and denominator. Change the sign of the second part, the imaginary part. Since it's plus here, it would be minus. If it were minus, it would be plus. And now you multiply. This is not the same as our problem up here. This is 1 times negative 5. And I'm going to do the last times the last, because it's 2i times a negative 4i. Well, that's a negative 8 I squared, but the I squared is a negative 1, so you add 8. Here's negative 10i and a negative 4i, which is a negative 14i. So our final answer, let's see, 3 minus 14i in the numerator. The denominator, this is the sum and the difference. This is the difference of two squares. So it's a negative 5 times negative 5, which is positive 25, minus, well, 4 and 4s and negative 4s and negative 16, but I times I is I squared, so it's a positive 16. And this is 3041. So you get your answer by multiplying. You didn't divide. This used the idea of a conjugate. Let's take a look at some of these properties of conjugates. Complex conjugates. So, let's suppose that z equals a plus bi. Let's suppose w equals c plus di. Then what is z with the bar over the top? That's the conjugate of z, a minus bi. What is the w with the bar over the top? W bar is the conjugate to c minus di. Here's some of the properties. What is z times z bar? Well, we can use this, let's see, a plus bi times a minus bi. There's a squared. That's a negative b squared I squared, so it's a positive b squared. All of a sudden, you can factor the sum of two squares. But remember, these others, abi, negative abi, cancel. So this is a squared plus b squared. Second property. One over z equals z bar over z times z bar. We can, I guess, go through the same process with these z's and z bars. I'll let you do that. Let me just write this down. Z bar is z. The fourth one, z plus w bar is z bar plus w bar. So you can split those up. And when you multiply, z times w bar is z bar times w bar. And you can confirm all those by using this a plus bi and a minus bi stuff. I guess we're not going to do that on this. I'll leave that to you. It might be in some of the assignments too. So, how do you work with these square roots of negatives? You pull your eye out. If this capital N is an element of the positive reals, that's 1, 2, 3, 4 to infinity. We define the square root of the opposite of n, remember n is now positive, as the square root of n I. Many times we'll put I out front so that it's not confused being underneath the radical. But this is what I mean if you ever hear me say, pull your eye out. Don't do that physically. If this is the square root of a negative, you pull out an I and then start to work with it. Now we can find all the roots to any quadratic. And they might say, find all real and complex roots. Because now we got if ax squared plus bx plus c equals 0, where a is not 0 because we want a quadratic, then x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Now this part underneath the radical is called the discriminant. The b squared minus 4ac. And if that is greater than 0, we know what these roots will look like without going through and calculating them. We know this will be a positive number underneath the radical. The square root of a positive number will be a positive number, and that means that we're going to get two answers. They will be real numbers, but they will be different because you're going to add something and subtract something. Suppose b squared minus 4ac is equal to 0. Well, I want you to realize every time you got a quadratic, you are going to get two answers. In this case, this thing will be 0 because the square root of 0 is 0. It will be real numbers. There's no square roots of negatives involved then. But these now will be the same. There's two answers, they're just the same. But it's important to recognize the two answers. b squared minus 4ac is less than 0. Well, once again, you're going to be adding and subtracting, so you have two answers. But now, because this b squared minus 4ac is negative, you'll take the square root of a negative, you'll pull your I out, you'll have a complex number. But it'll be important that to recognize this is negative b plus that, negative b minus that. These are conjugates. So without even calculating what the values are, we know how many, it's always two, whether they're real numbers or complex numbers, whether they're different, the same, and if they're complex, then it'd be conjugates. So, let's do some examples. This is number 16. Sorry, I've moved that down again. Goodness. There we go. Number 16. Write in standard form. Oh, we never talked about that. Standard form for complex numbers is a plus bi form. So if you're given something sort of simple, negative 4 times the complex number 2 plus 8i, they just want you to multiply things out. This is a negative. Now if you need 4 steps, this is 2 steps, right? So a negative 4 times 2, because we're going to distribute this, plus that negative 4 times 8i. So if you need 4 steps, you need this sort of intermediate one, negative 8 minus 32i. There's your 4 steps. Number 44. Same directions. Right in standard form, but now we have 2i to the 4th times 1 plus I squared. So let's see here. We distribute this, we get 2i to the 4th times the 1 plus, and I won't put that in extra, but this is 2i to the 4th times I squared. So now you get 2i to the 4th plus, well, this is 2i to the 6th. Let's see here. I to the 4th. Let's see. I to the 0 is 1. I to the 1 is I. I squared, negative 1. I cubed, negative I. So I to the fourth is just a 1. So this is 2 times 1 plus 2I to the fourth. Fifth, sixth, I to the sixth is a negative 1. So you might put those down here. I to the fourth, I to the fifth, I to the sixth. And then finally this is 2 minus 2. All that work to get 0. Number 52, perform the indicated operation. On the square root of 4 plus 3i times 3i minus 4. Now you can do this several different ways, but I guess I'm going to do it sort of the brute force and not do any really slick tricks. This is 4 times 3i, so it's 12i, and 4 times a negative 4, so negative 16. 3i times 3i is 9i squared, and 3i times a negative 4 is a negative 12i. So let's see here. 12i and a negative 12i. So now we have the square root of a negative 16 plus, this is 9 times a negative 1, which is a negative 16 minus 9, which is a negative 25. When you see the square root of a negative, you pull your I out. So this is really, even though we put the I first for the square root, when you just have a number, it's also standard practice to put the I afterwards. And we got our steps. But now if we solve an equation, we can get maybe all the solutions, don't have to worry about square roots and negatives. This is number 72. Solve, and we'll say probably on my tests, over the set of complex numbers. If you're not told what set you're supposed to solve this over, then you assume the real numbers. When I say the complex numbers, we go that extra step. X to the fourth plus 3x squared minus 4 equals 0. Now you can do this by factoring. The factors of 4, the subtract, give me 3. I can do that, I think. So it's x squared times x squared. And 4 times 1, we know the signs are opposite. So we must be positive, because that's a positive 3 and a negative. So we keep factoring if we can. This is still x squared plus 4. But this is the difference of two squares. It's x plus 1 and x minus 1. And now that we've got this equal to 0, each of these factors can be set equal to 0. X squared plus 4 equals 0. X plus 1 equals 0. X minus 1 equals 0. These are real numbers. X equals 1. X equals a negative 1. This, we're going to get x squared equals a negative 4. So take the square root of both sides. X equals, don't forget the plus and minus, but now we got the square root of a negative 4. So x equals, well, pull out your I, so plus or minus I, and the square root of 4 is 2. So this is really plus or minus 2i. So these two and these two are the 4 that we should expect when we have a degree 4 polynomial. Suppose you didn't want, and you'll be asked to not solve this, but we just want to, they say, determine the character of the solutions for number 78. So the character of 4x squared plus 12x plus 9 equals 0. What is A? 4, B, 12, C, 9. What is B squared minus 4AC? That's 12 squared minus 4 times 4 times 9. So you get 144 minus, what's 16 times 9? 9 times 6 is 54, 9 and 5 is 14. Ooh. The discriminant is 0. So, if b squared minus 4ac is 0, remember, and this is the way I guess I remember, it is just that square root there, b squared minus 4ac over 2a. If this is 0, it's just really a minus b over 2a. I get 2 real same roots. Don't know what those roots are, but I know there's 2 of them. I know they're real numbers, and I know they're the same. One last one with our conjugates, number 84. If z is equal to 3 minus 4i, and w is 8 plus 3i, and we want to write this in a plus bi form, or standard form, what is z minus w conjugate? Let's see. It's the z, or 3 minus 4i, minus w, 8 plus 3i, conjugate. So it's 3 minus 8, or negative 5, negative 4i minus 3i, or negative 7i, conjugate, which is a negative 5, leave the first one alone, change the sign, it was minus, make it plus, 7i. Does this make sense? Okay, we'll see you in the next section.